Um, what we have to talk about today is just this continue like the discussion like we started yesterday about the fixed point theorem. So let me share my iPad. Okay, so let's see. What is it that I was telling you yesterday? The idea of like a fixed point of a function, if you have a function, a fixed point is a point where if you the function does nothing to it, so that it is fixed by the function. That's where the name comes from. And we did like a picture like yesterday, like oh sorry, let me just shrink my okay. Okay. So we did like a picture yesterday of like, if you look at the graph of the function, like let's say the graph, you know, is y equals f of x. Well, what a fixed point means in this context, right? If you draw the line y equals x, maybe they will meet here, like just like extend. Right? A fixed point is basically where the two graphs or the two curves intersect, right? So in this case, there's like a point of intersection here, so this would be a fixed point. There's another point of intersection here, so that would be another fixed point, right? Um, Let me see if I can extend the x-axis for a little bit. Um, there's another point of intersection here, so that would also be a fixed point, right? So like at least for like what I drew with this graph, there are three fixed points. There could be more, like depending on how the graph looks like, right? But so in terms of like what like the function does to a fixed point, like the idea is that it basically does nothing to it. It kind of like leaves it as it is. And it's kind of like also easy to kind of like come up with examples of functions that have no fixed points. So for example, so like the one I had said, maybe I think this was like yesterday, right? Like that f of x equals x cubed has three fixed points, right? I think we had done that example. The fixed points in this case were 0, 1, and -1. But if you kind of play around with the graph, it's easy to come up with cases where like there would be no fixed points, right? So for example, something like what x squared plus 2, if you look at the graph of like x squared plus 2, that's going to be like a parabola, but that's kind of like always like above the y equals x line. So like those are not going the graph is not going to have a fixed point, right? So this one has, which you should be able to corroborate, right? Because like you would try to solve, you know, otherwise, you try to solve that x squared plus 2 equals x, and that is like a quadratic equation, right? And like that one has like like if you remember complex numbers, that one has like imaginary solutions or like complex solutions. It doesn't have like it has no real solutions, right? Is that making sense? So like all that I'm trying to say as of now is that there are functions, some which will have fixed points, others will not, and kind of like what we want to discuss in more detail today is like what can you ask of the function so that they're like fixed points of that function. Okay, so it kind of like is just like what conditions would guarantee that the function has like at least a fixed point? Okay. Um, is that making sense? Questions up to this point? Anyone? So what I was saying yesterday is that one condition that ends up being useful to guarantee a fixed point is if the function is a contraction. So I'll remind you what what the property was. So like let me give this as a partial answer because it's not the end of the story. You still have to say something else. So and being a contraction, what it meant, I'll do the picture first, maybe, just for starters. Like what being a contraction meant is that if you have like the graph, let's say you're like maybe you're studying the function not on the entire domain, but just like on some interval. Like usually we work on intervals here, but let's say you have like an interval a comma b. So here's like your interval. So being a contraction just means that if you take 2 points on that interval, like let's say x1 and x2, if you take 2 points on that interval, you know, they give you corresponding points on the graph when you apply the function, and they give you some corresponding y values, right? Okay, this one ended up being a nice picture. So a contraction just means like the function would be a contraction. It's kind of like the distance between the points in the domain, like x1 and x2, is larger than the distance of the values of the function. Like usually that's called like the images. Like so the contraction is at on an interval a comma b. What you have, and remember distance can be measured in terms of absolute value. So f of x2 minus f of x1 is less or equal um, than a constant times x2 minus x1. Well, times like the absolute value of x2 minus x1, where k is like some constant, some positive constant less than 1. That's kind of like the definition that I had given you last time. So it's basically it shrinks the distances, like the images have their distances shrunk by kind of like at least some fixed amount. So, it's kind of if k for I think that's kind of like the example I was doing yesterday. If k happens to be point 5, that means that the distances in the image are never more than half the distances like in the domain, right? So like it always shrinks it by at least a factor of one half the distances. So it's kind of like you'll see like in a couple of minutes that is like a useful condition to have um on the function to like guarantee that there will be a fixed point. Um is that making sense up to this point? So far so good. And here's like a more interesting question also, like what like it seems like a rabbit hole, but what condition on the function makes it a contraction. So when do you have a function that happens to have this contraction property? And there's an easy answer you can give in terms of the derivative of the function. So like that's kind of like also useful to have uh, outside this context, right? It's like a useful piece of information regardless of like this particular topic of the fixed point theorem. So this is like a useful result if the function, if the derivative of a function satisfies. So if the derivative in absolute value is always less or equal to k, um, for some constant k less than 1, well, like it's a positive constant, so then the function will be a contraction on that particular interval. Then f of x is a contraction on this interval. I'm about to justify it because it's like actually a one-line proof, so it's kind of like cute to see. But like before, like writing it down, like the proof, it's useful to think about what this says because if you remember, like the derivative it tells you information about how the function is changing, right? Like it is a rate of change. So it's kind of like the speed at which the function, like how fast the function is changing. So if you're saying that the derivative is always less than 1, well, like in absolute value, that means that the function, like that kind of like constrains how much the function can grow. You know, again, it's like if you think about it in terms of position and velocity, if you're saying that you're always driving at less than 1 mile per hour, that tells you like something about how far, like, how much you can travel in a given amount of time, right? So what the result is saying is that if as long as your derivative doesn't grow too fast, like the function will kind of like shrink the distances, like of the points in the image. Is that making sense kind of intuitively? Like, I'm about to justify it anyways, but but it's a useful thing to know, like outside like our discussion about the fixed point theorem, that you know that controlling the derivative basically controls how much can the function change in values. Uh, so and then I'll do an example of illustrating this fact um, to show you how you use in practice. But here's like the reason why is this true. It is really because of the fundamental theorem of calculus. So why is this true? So there's this very clever trick using the fundamental theorem of calculus. It looks silly, but if you have 2 points like f of x2 minus, and if you have x1 and x2, and you have 2 points, and you'd subtract the function, like the difference of the function at those 2 points, like do like f of x2 minus f of x1. That is the same as the integral from x1 to x2 of f prime of x dx. So it's useful to kind of like think for a second why this would be true, right? That's kind of like just what the fundamental theorem of calculus says, right? Because what's that integral of f prime? It's kind of like an antiderivative, right? Like, so the integral of f prime is just f, right? So the integral of this is just f, and this is like a definite integral. So you just evaluate it at the endpoints, and when you evaluate it at the endpoints, you get f of x2 minus f of x1. Is that making sense? So let me just say that this is like the fundamental theorem of calculus. Because again, like, how would you integrate this function? How would you integrate the derivative? It's just like the function itself is like the like the antiderivative. So you evaluate it at the endpoints, which are x2 and x1, and then subtract, and that is the same. So, and like what that tells you, like, but it is like useful what it's saying, because it's saying it's giving you like a way to compare the value of the function at two different points in terms of like the derivative. Maybe I should put it like in terms of the physics interpretation, right? Like if you think about it in terms of physics, is that like like the position at time two minus the position at time one, that would be the integral from time one to time two of the velocity, right? Or let me put it like as the xt. Right, like because it's saying like the change, like what is x of t2 minus x of t1? That would be the change of position, right? So what this formula is saying is that the change of position, how do you find the change in position over like a certain amount of time? You just integrate the velocity vector. Well, I'm saying velocity vector, but this is like in one dimensions. You just integrate the velocity over that amount of time. Is that okay? Is that kind of like reasonable? Uh, is that plausible? Like just double checking. So the change of position is like the integral of the velocity, right? And like the version like with derivatives is what I wrote above. So then what you do is you take absolute values on both sides of the equation, then take absolute values. Okay. And then I don't know if you have seen that before, but there's like a very useful property of absolute values with integrals, which is that you can kind of like move the absolute value inside the integral, and that increases it. So this is called it's kind of like a version of like something that's called a triangle inequality. Basically, what I'm saying is that you can move the absolute values inside the integral. And that is basically what you need to use, because now by hypothesis, this derivative in absolute value is never bigger than k, right? Like the assumption was that our assumption is that this derivative is less than k. So by some assumption, I'm going to use now that this is always less or equal to k. So, well, yeah, it's also like an inequality. But that is just like integrating a constant, right? Like the like the integral of a constant is k times x2 minus x1. I mean, I'm assuming that x2 is bigger than x1, but like I'll put it in absolute value, just so that it looks exactly the same as how I wrote it in the statement. Okay. So if you put everything together, that tells you that f is a contraction on this interval. I'm about to do an example with a particular function so that you see how it works. But is that kind of making sense? Questions about this? Oh, I mean, I just put it like it's not necessary here because when I did it, I implicit. I mean, you could put it like you could put it without absolute value, right? If you want. It's just when I did it, like like when I did the calculation, I'm assuming that x2 is bigger than x1, so it, the absolute value makes no difference. It's just that that way it looks identical. You know, it looks identical to how I wrote it because the way, like like the way the formula for the contraction is like written down. Uh, x2 minus x1 is in absolute values because you don't know which one is bigger than the other, right? Like, x2 could be, the way I'm drawing it on the diagram, x2 is always to the right of x1. But in principle, like if x2 were less than x1, then, there's kind of like an overall minus sign. So, but the absolute value doesn't notice that because, it just gets flipped. So I just put it there so like that so that it would look exactly, it would look exactly as like how I wrote it with the condition of being contraction, but it's not necessary here because I did this assuming that like x2 was bigger than x1. You see, so you can leave it without the parentheses. Like otherwise, the thing is like or let me put it like this: if I write it like this, then like I'm already assuming that like if you put it like this, then you're assuming that x2 is larger than x1, because if you had like kind of like an integral from 3 to 1, that would be negative, right? So like that, like that would have to be flipped. So that kind of like is an assumption like implicitly here uh, that I'm using. But if x1 is bigger than x2, then you do the same argument, but like you do f of x1 minus f of x2. It's just kind of like silly to put it like that. It's kind of like to avoid cases, all that I'm saying, because like strictly speaking, you have to do a case where x2 is greater than x1 and where x1 is greater than x2, but it's completely symmetric. So like, like once like doesn't matter which one you call x2 and x1, you can always call them like x2, you can always call it the larger number. Uh, okay, let me do an example just to show you how like this works. So let's say, um, okay, here's an example. Let's say you have this function square root of x, which we all know. Or I'm using red for the function. Okay, so here's like a question I could ask. On which interval is this function a contraction? So this could be like a question. Find an interval on which f of x is a contraction. And maybe let me draw the graph of absolute value of x so that you remember it also. So because of what we were saying, if you're trying to find an interval where the function is a contraction, you might as well look for an interval where the derivative of the function is always less than one by some fixed constant. Okay, so the way I would do this problem is like what I'll do is I'll try to find an interval where f prime of x is less than some constant k, which is less than one. Okay. Oh, actually, let me do it with two root of x. It is just, I mean, it's more or less the same thing, but it just makes my life easier because then when I take the derivative, like like the twos cancel out, so it's a little bit nicer to work with that. Okay, so what is the derivative of the function two root of x? Okay, so what is f prime of x? Well, that's the derivative of two root of x. The constant comes out of the derivative, right? So it's just the derivative of 2 times the derivative of root of x, which is 1 over 2 root of x. Hopefully you remember that, right? And this gives you 1 over root of x, right? So that is f prime of x. So you see, like having the 2 in front just kind of like is nicer so that you can kill off um, the twos. Okay, so that is a derivative, right? So we would like this derivative to be less than one. So immediately that does tell you that there are like like certain things that you like have to avoid, right? Because if you put like a number x, right? What happens if you put a number x that's very, very close to zero, right? If you remember, like division by zero, like if you put like a zero in the denominator, that kind of like tends to blow up things, right? So that definitely tells you that you should avoid like the like points of x like closer to zero, right? In fact, like you should even avoid anything between zero and one, if that makes sense, right? Is that making sense? Because in that, if you can, well, first, like you can evaluate the derivative at zero, or you can think that the derivative at zero is like infinity, right? Because like the tangent line is completely vertical, so the slope is completely vertical. But if you put anything between zero and one, this derivative will be, will be like a number greater than one, or it could even be one, right? If you put x equals one, then this derivative becomes one, but for the contraction, the number that you find is strictly less than one. Is that making sense? So definitely, like the interval cannot, whatever the interval is, it cannot include like um, anything like, you know, which is anything that in between zero and one. Okay, but that is kind of like basically the only restriction. So, for example, if you move a little bit away from one, that is going to be already like in the safe zone. So, for example, like here's like but anything else like works basically, but anything else more or less works. So, for example, let's say that you take for example the interval 1.5 to like I don't know to infinity. Okay, like there's nothing special about 1.5. It's just I wanted like an interval that like avoids one, so I want to start it somewhere. Like where like the derivative doesn't want to get close to one. So if you put like if you take this interval, then what happens? what happens with the derivative, right? Then on this interval, uh, x is always greater or equal to 1.5. So if you take square roots on both sides, you get this, right? Yeah, you can take square roots on both sides, and then if you reverse the inequality, you get this. But what is 1 over root of 1.5? Like, you can compute that like if you want, but like actually, if you want, like we can do the calculation. Let me see it. Put it here in Wolfram. What is 1 over square root of 1.5? Uh, that is like around 0.80. Like this is roughly like 0.16. Okay. So that would be. Oh, okay. That's a great question because if you put like I'm about to answer that, but this would be the K. Okay. So yes, what happens? What happens? What happens if you choose like the interval? What happens if you use 1 to infinity? Okay, you kind of like run the same argument. So on this interval, right? Then 1 is less than x, right? So you take square roots on both sides. So 1 over root of x is less than 1 over root of 1, which is 1, right? So it tells you that the derivative is less than 1, right? But uh, it doesn't tell you, like, when you say that like the function is a contraction, like the bound on the derivative has to be slightly less than 1. Because here, like, you're letting the derivative get closer and closer to 1. So there's no safeties. Like you need like a buffer zone. So you need like the derivative to be kind of like it cannot be allowed to get as close as you want to 1, if that makes sense. You have to kind of create like some region of like of protection. So this is like getting close, it's always less than 1, but like arbitrarily close to 1. So that's like the difference. So this one doesn't work. Given how we define the contraction work, since these values for the derivative get as close as you want to 1. Is that making sense? So basically, when you have a contraction, what you want the derivative is not just to be less than 1. You want it to be less than 1 by some fixed amount, um, which is how I wrote it here. Oops. When I wrote it here, I wrote that the derivatives had to be less than k, where k was less than 1. But it is always kind of like you're not allowed to get close to 1. So there's nothing special about 1.5. I just chose 1.5 just because that gives you some buffer zone from 1, right? In fact, any interval like that starts at 1 plus some amount, in fact, like any, in fact, any interval like of like 1 plus some tiny amount, which you can call h, comma infinity would work if h is some positive number. Like, the only thing that is not allowed is to like literally, you have to just create some buffer zone from 1. But uh, but besides that, like you like that's okay. Like you can, you know, you don't have to like you can choose like some wiggle room basically. Is that making sense? Okay, so now what I'm going to explain is kind of like how do you okay, so we're basically ready to state the theorem, but before we do it, what I'm going to give you like an idea is like of how it works. So basically what we're going to show is like when the function is a contraction, there will be a fixed point on that interval, provided something else happens, which I'm about to write. But basically, the way you would do this is by providing a sequence that approaches the fixed point. So what I'm going to do first is just kind of show you how the sequence is constructed, and then I'll write things down in detail so that you have it more precisely. But let me show you the animation first because that's kind of like it's better to go into the theorem with some perspective of how it's supposed to work. So I did it on GeoGebra a bit earlier. Okay, let's see. Let me see. Can everyone see the GeoGebra animation? So here, what happens is that you have a function like the green one, okay, um, which is 2 root of x. That's why I chose like that function earlier in the example so that I could just apply it to this case. So you have the original function, right? Then you have y equals x, and so the fixed point, right? The fixed point you can see here. Like for this case, it's obviously something you could do by yourself. Like you don't need any fancy technology, right? But the fixed point here, what would be the fixed point? It would be 4,4, right? That is a fixed point in this case. Let me put it like even in you know a different color and everything, right? Okay. So let's do this here. I think I used this. Okay. And okay. So that is the fixed point, and those are so that is what we would like to try to find, right? So I want to find this point on the graph, right? Or like this x value. Once you have the x value, obviously you have the point on the graph because it will be a fixed point. So you even will know the y value automatically. It's going to be the same. That's why I'm showing you here the x value. Can you see my pointer, by the way, on the GeoGebra uh, animation? Uh, so like the idea is that on a fixed point, the x value and the y values coincide. So like they are here. Okay. So um, so how does like the process start? So the idea of like the algorithm is that you start with a random point on the interval where the function is a contraction. So as we were saying, like the function is a contraction, like everywhere, like between like anywhere like I did it with 1.5, right? So anywhere like to the right of 1.5 the function was a contraction, right? um so you start where like with the point where the function is a contraction, okay? And so like, I choose like a random point like 2, okay? So I choose like an x value which is 2, and so here like you like that's the first point in the sequence, x1 equals 2. Can you see this, by the way? Like just double checking. Okay, so once you have 2, like which again is like a random starting point. Okay, that's like arbitrary. There's nothing special about 2. It's only the fact that it was in the safety zone of where the function is a contraction. Once you have 2, then you find the value of the function at that point, right? So you apply f of 2. Okay, f of 2. Like actually, let me draw this like as a broken line so that it's not confused with the graph, right? Like the graph is a green curve, y equals x is just like the identity, right? So f of 2 is gives you this point on the graph, okay? And you collect the y value. So you keep track of the y value. So the y value in this, oops, sorry about where is the y value here? Ah, here it is. Here's the y value. Sorry. So this is the y value corresponding to this point. Okay. And in step two, you're going to use that y value as the next x value. So that's what I'm going to show you here. Okay. So like I'm trying to follow with the colors. I use the correct color scheme. So you start with the point, you find the value on the graph, you record the y value, and then you use that y value as your next x value, which is what you see here. If you see that I'm saying that x2 is going to be f of 2. Okay. So once you have that second x value, you kind of like iterate the process. So you find the point, the corresponding point on the graph. So what is the corresponding point on the graph? Is this one that you see here now in orange. Okay. There's a corresponding y value. Okay. The y value is this one. And you use that y value as the next x value, which would, sorry, would give you, where is the next x value? Is it no? Where are you? Oh, here it is. Sorry about that. Is the process making sense? So kind of like you apply the function, and then you use that as the next x value. So if you see like the sequence here is like you start at 2, then the next x value is f of 2, then the next x value is f of the previous step. So it's f of 2. Um, okay, and then you do the same one more time. So you find for this point, you find the corresponding uh, point on the graph. The point on the next point on the graph is this one. Okay, you you record the y value. The y value is this one now. Oops, sorry, is this one, and then you use that y value as the next x value. So the next x value would be here. Okay, and so the fourth point would be f of 2. Okay, and kind of like you can kind of like see it here, like the x's, like the x values seem to be kind of like moving towards like the fixed point, right? And that is kind of like what we will show will happen. But kind of like the algorithm is like you start with a random point and you start applying the function f to that random point. So it's what people call like iterate the function on that point. Is that making sense? Kind of like the idea of like the method. Is that the animation kind of like plausible? So, and you'll see in a moment why where the contraction hypothesis is being used, because basically what you want is for the points, the x values. You kind of like see it here, like the x values are getting closer and closer to one another, right? If you start zooming in, like like these are like this is like the different distance between the original two x values, then the next two x values. This is their distance, and then there's the distance of the next two, and kind of like the idea is that the x values are getting closer to one another because it's a contraction, and the x values are the previous y values. You see, so that kind of like starts shrinking everything into like trying to force it to converge, basically. Is that making sense? So the only hypothesis which I'm about to write. So if you look at this algorithm, the other besides being a contraction, the only other hypothesis that you really use is kind of like the fact that you can kind of like you need to be able to continue applying the function f to the previous values. So basically, what that requires you is that kind of like the values of the function are contained. The values that the function can take is contained kind of like in the domain that you chose, because otherwise you may run into the issue. Then when you evaluate the function, you would get like outside the safe zone and like drops land somewhere else. So the only assumption would be that when you apply that function to a point, that gives you a point that was inside the domain, so that you can keep applying the function to it, which is like it's fine in this case. Like that does continue happening. So like but let me write all of this down so that you can have it here. Well, actually, let's take a 5-minute break, and when we that way I can answer questions just to see if anything else is like occurring. And then after the break, I'll write down the fixed point theorem, prove it for you, and that will be the end of today's class because then you have to take the. I'll give you the quiz for you to take. So, but let's say like a 11:21, in case someone wants to ask me something else, I'll just like. It's useful to have like a mini pause before we write down all the details. I'll pause the recording for a second. Okay, I guess we can continue the discussion. So again, we're almost there. I'm just going to like write it down so that you see like the details. But let me share my screen again. So here's something useful that I haven't said, which is also a nice result to have on on its own. So not, here's another useful fact. And after I write that down, I'll show you like the proof of the fixed point theorem. So the fact is that if a function is a contraction on a particular interval, then it can only have at most one fixed point, okay, on that interval. If a function is a contraction on an interval, let's call I the interval, then and there is at most one fixed point, okay? That's kind of like useful to know because that way that means that you cannot find two fixed points, for example, or three or four on that particular interval. Okay. And again, why is that true? So why is this true? And so this is kind of like a classic proof by contradiction. Um, Basically, you assume that there are two fixed points. So and see what goes wrong. So let's assume by contradiction. So this is called like a proof by contradiction if you have seen those before, which probably at least you have seen maybe once or twice, like this type of proofs. You assume by contradiction that there are two fixed points on that interval. Again, whenever I write like a fixed point, I'll try to decorate it with like a star or something like for just to say that it's like a special point. And what does it mean to be a fixed point? It means that the function does nothing to it. In other words, let me write this in a different color, just so you have it here. So in other words, f of x1 star is x1 star, and f of x2 star is x2 star. That is what it means to be a fixed point. Again, that the function does nothing to it. Is that making sense? And so and then what happens here? So what is the distance between the 2 points? So then notice what is x1 star minus x2, or what is x2 star minus x1 star? Well, because they're fixed points, that is the same as f of x2 star minus f of x1 star. Right, like that is true because the points are fixed points. So that what that means is that there's no difference if you apply the function to it. Okay? But because the function is a contraction, right? If the function is a contraction, this distance is shrunk by an amount k. Okay, so because the function is a contraction, this is less than k times x2 star minus x1 star. Is that making sense? So what that's saying is that x2 star minus x1 star is less or equal to k times x2 star minus x1 star. Okay? And if you divide both sides by this absolute value, that means that one is less or equal to k, which is not true, right? Like the contraction is like shrinks everything, right? Which is like impossible. So that is, it's like a cute proof. I mean, it's like a not too bad, but it's like an interesting proof because it's like that shows you how you can use all these different types of information like simultaneously. So that's kind of like a useful piece of information because it tells you that when you have a contraction on a particular interval where the function is a contraction, then there's at most one fixed point. Okay. And then when the fixed point theorem is to guarantee that there is a fixed point, but then there has to be a unique one because of what we just proved. Okay, so it's sometimes useful to know that there's like a unique solution or a unique fixed point, and this is what like we will have from the fixed point theorem. Is that making sense? Okay, so let me finally write it down. Okay, so here's like what the fixed point theorem says. So the idea is that suppose that you have uh, a continuous function which is a contraction on some interval. I'll call just like the interval I. The interval could be open, could be closed, could be include infinity. It just has to be some interval. Um, And like the only thing that we do need as an extra assumption is that what I was telling you, like when I showed you the animation with the GeoGebra, is that um, the values of the function are contained within this interval. And furthermore, f of x belongs to this same interval for for any for any point on the interval. That is in practice is not that bad. Like, it's not as important. Like, like that is usually easier to check. But like like when I write down the sequence, you'll see that that's useful because like it's what allows you to keep like applying the function to the points. Uh, then the claim, let me write the sequence in a different color. The starting point is like arbitrary starting point. And then once you have the arbitrary starting point, you start hitting it with f. So you take f of that point, then f of the previous of the next point, and so on. So and the end step xn is f of xn minus one. Okay. That my claim is that that sequence converges to the fixed point of the function on this interval. Then the sequence to the unique. Well, let me write it like this. Um, then there is a fixed point on this interval, and and this sequence converges to it. Okay. Let me see if I can show the entire statement. Okay. I'll give you a chance to copy it. Or let me actually write it in a different way. I'll write it as saying that this sequence converges and the limit is at the fixed point of the function. Like it sounds less confusing this way. Then this sequence converges to a to a number x star, and x star is the fixed point of f on this interval. That sounds less confusing. Okay. Is the statement making sense? Like, is it clear what it's saying? So essentially, what I'm saying are two things. What I'm saying is that this sequence, there are two claims in this statement. The first claim is that this sequence converges, and the second claim is that what it converges to is a fixed point. So it's useful to understand that there are two separate claims. So let me write that down. I'll kind of like the second one is a little bit easier to understand than the first one, so I won't kind of like go into too much details on the first one, but I'll give you some idea. So there are two claims here. So the two claims are two claims being made. The claim one is that the sequence xn is convergent. And x2 is the claim that the limit that xn converges to is a fixed point. I mean, in principle, obviously this would have been silly, but you could have produced a sequence that converges, but not to the fixed point. Obviously, that would have been interesting, but that is a theoretical possibility, right? So you like there are two things like that in theory you would need to check that is that this does converge, and the second part that the convergence is a fixed point. Okay, so I'll kind of focus more on the second one and give you an idea for the first one because like the first one is a little bit more tricky. But why is the second claim true? Why is two true? And this is like the cool thing about having like a formula for the sequence, which is recursive. Remember, like a recursive formula. A recursive formula is one where like an element of the sequence is given in terms of the previous elements. So because of the definition of xn, xn is f of xn minus 1. Okay. And once you have that, if you know that the sequence converges, which I'm assuming that for the moment, if you know that the sequence converges, you can then just take limits on both sides of the equation. So you take limit as n goes to infinity of xn. That would have to be the same as the limit as n goes to infinity of f of xn minus 1. Okay. And again, this can be done because you can take the limits because you know that the limit exists. That presumably is what you prove in part one. Uh, it, you have to show first that it converges, but if you assume that for a moment, I'll say why that would be true. But if you assume that it converges, then you are allowed to take limits on both sides of the equation. What would the left-hand side give you? That would just give you the value of the limit, which is I'm calling x star. And what happens with the other one? Well, because the function is continuous, then you can evaluate this limit just by moving the limit inside the function. That is what being continuous means, that you can just kind of like move the limit in. And actually, this is the sort of thing that we talked about on the first day of class when I told you a little bit about sequences. The limit of this sequence is the same limit as the limit of xn, because this sequence is just one step behind xn, so it will converge to the same limit. So this will give you that x star equals f of x star. So that is a fixed point. So it's like a very elegant argument once you know that the sequence converges. Oh, that can be done because that's like the definition of being continuous. So this can be done because f is continuous. Uh, that is actually one way to define a function to be continuous, that you can do this. Like that's actually the definition of a function being continuous in terms of like sequences. So this is because f of x is continuous. Like it probably that's not the way it was spelled out in Calc 1, right? Because in Calc 1 you had not seen sequences yet. But I mean, it takes some time. Like that's it's not too bad, but you can double check that if the function is continuous, like kind of like what that means is that you can kind of like move in the limit inside the function. That's how like it works. That's actually something that you would have used implicitly when you were doing L'Hopital's theorem, when you were finding limits of derivatives and things like that. Like it does use a continuity, like a lot of the time. But it's just basically whenever the function is continuous, you can kind of like insert the limit inside the function. Um, which actually, like, if you think about it, it's something you kind of have done. I'll erase this in a moment, but it's something you kind of like implicitly do without thinking too much about it. Like if I ask you what's the limit as x equals 2 of cosine of x squared, right? I think you would say like cosine of 4, right? Like that would be my guess. But why can't you say cosine of 4? Because literally you move the limit inside, you see. Is that making sense? So I mean, I will erase this, but that's kind of like it's so used that you don't even realize you're using it, if that makes sense. But essentially, if you break it into mini steps, what you're moving is the limit inside the cosine. Like it's just that people don't even write that because it's kind of like so intuitive that it kind of like seems a bit more confusing if you write it that way, right? But that is literally what you're doing, like moving the limit inside the function. And whenever you can do that, that is precisely like the definition of a continuous function. So I'll put this as an aside, just you know, just to illustrate that fact. It has it has nothing to do with the proof of what I'm discussing. It's just like to illustrate how continuity works. And then, okay, and that explains why the limit would be a fixed point. The only thing that's left, and again, I won't go into too many details because it's too much like of a proof thing. But like why does the why does the sequence converge? So then this claim one, and this is exactly why on first day of class I told you, oh, when you have a sequence, it's useful to know that a sequence converges, even if you don't know what the limit is, right? And so I told you that there's like a name for those sequences. They're called Cauchy. So essentially, and I'm not going to do this right now because it takes more of a detour. But essentially, what you have to show is that the sequence is Cauchy. Once it's a Cauchy sequence, it automatically converges. That's kind of like the property of a Cauchy sequence. So kind of like the idea, but again, I won't say more than that, is that you show that the sequence Xn is a Cauchy sequence because that guarantees that there's a limit. That will automatically guarantee convergence, which will guarantee convergence. And what the to show that it is Cauchy, you do have to use the fact that the function is a contraction. That is where like the contraction gets used. But again, like it's a little bit more technical, so I don't want to do it because there's no point. Like, right now it's like a bit it would be too confusing. But to show it is Cauchy, you use the fact that the function is a contraction because basically that would start doing is like shrinking the distance between the elements of the sequence. But again, I won't give more details than that because that is a bit more like advanced. Um, like because it does require being more like comfortable with sequences and proving like inequalities and things like that for sequences. But it kind of is a good summary of many of the arguments in this course, where it's like you construct a sequence. That's kind of like what happens most of the time. You construct a sequence. You want to show first that the sequence converges. To show first that the sequence converges, you show that it is Cauchy in some way. Once you know that, then you show that the limit has like the properties that you desired, that you were after. So it's always like a two-step process, like most of like the constructions in this course. Like you come, I mean, of course, like step zero is the most important one, which is like the clever idea of how do you build the sequence, right? That is not like, that is kind of like the part of the imagination. Because once you construct this, like once I give you like the formula for the sequence, then you can start like analyzing the properties. Obviously, just like who comes up with the idea of like let's define the sequence this way, that is also like super important because otherwise like there's nothing to prove. But that is kind of like more of like creativity, so it's like but once you have the sequence, however you come up with it, you prove it's Cauchy. Once it's Cauchy, it has a limit. Once it has a limit, then you show that the limit is supposed to satisfy the properties that you would like. Okay, is that making sense? Okay, so let me see. I think this is a good place to end. So what I'll do, let me see if I can share my Firefox screen for a moment. So basically, okay. So as I was saying, like right now, like let me see if I can make the quiz available. I'm going to make available the quiz. So now you should be able to take the quiz. Like to take the quiz, you do have to log off out of Zoom. So you can take the quiz, use the responders. Hopefully that went well when you practiced it yesterday. And once and again, remember to do the quiz on a piece of paper. And then once you are finished, like solving the quiz, then you go to the assignment. You go to the assignment and then you upload the quiz solutions for that. But like, there's no more class today, obviously, because like like that would be too confusing. So you like like I gave you 30 minutes to take the quiz. I think that's more than enough time. And then like after you're finished doing the quiz, like then you have like these 10 minutes to upload the solutions. Like it should be a really fast quiz because there's not much to do. But it's mostly for you to kind of like get used to like doing the quizzes online and things like that. But yeah, so for today, that's like the only thing I wanted to say. Although I will still stay around for a few more minutes if someone wants to ask me something before they take the quiz. That's also fine. If not, you can just go ahead and take the quiz. Well,